So in the last video, we went over Fourier series, and Fourier series um, kind of makes sense now, right? You can make anything, any wave with a bunch of sinusoids, and let's do one just for review. So let's say we want to make a triangle wave. This is actually a sawtooth wave, I believe. So you can actually replicate this with waves. So you'd have something like this. And remember the Gibbs phenomenon? It's going to look like something like that, maybe. Probably the center one is the best depiction of it. You can even model any piecewise function. So that means you can make something like this. Let's say parabola. Well, it's probably going to look something like this. It's a little bit hard to imagine what it would look like. So that's good. Now, for something constant, so let's say we have something like this. So that's the x-axis. Say we have something like this, right? So this is just y equals 1. What sinusoid frequency do you need for this? Well, if you think about it, if you have cos 0, what does that equal? It equals 1. And really, cos 0 is cos 0x. So any x you have, so you have x equals 1, x equals 30, doesn't matter what you put in, it's always going to be 1. So this sinusoid you're going to have on is going to follow it perfectly, accurately, with only one sinusoid, which is amazing. But what does that mean? Well, if you only use one wave to make your function, that means your Fourier transform is only going to have one wave. So here's where things get a little bit tricky, and hopefully I can help you understand what this can mean. So let's try to plot this in frequency space, and don't worry about it. It's not hard. It's hard to understand, but once you understand it, it's not too hard to understand things later. So for this graph, right? So this is time, and this is just amplitude, right? Now the thing is, for time to go all the way to, so in time, this function doesn't change at all. So what does that mean? Well, you can have one frequency make up that function. So in this case, the frequency is 0, right? So this is the frequency. So this is frequency graph. Now, this is probably very confusing, so let's do something else. Let's change it up a bit. Let's say we want to do, this is time again, so a time versus amplitude graph. Let's say we want to make just a sinusoid. So we have this function that's just sine t. So how do you represent sine t in the best possible way with a Fourier series? You literally just need sine t. So you can follow it accurately, probably more accurately than I am depicting. So your frequency graph will look like this, with the frequency you have over here, so this frequency being what you have here. So let's say this is omega, actually, because omega is just the frequency but with a term of 2 pi in there. So let's just have omega in this. This is still frequency, remember. It's just another letter. And omega is right over here. But this is 1 omega, right? So 1 t means it's omega t, where omega equals 1. So this is going to be 1. Okay? So that makes sense, right? Because you're in frequency space, you have the omega, your frequency, being only one straight line. So this is like, let's say 100%. So 100% of your wave is depicted by one frequency, which is the frequency of 1. Now, let's go back here and look at this. So now here, we have f, or let's replace it by omega now, is 0. And that makes sense because you only have one frequency, which is 0. Right? Okay. So let's try something a little bit different. Let's try this. So this is a sine wave, sine t plus 1. So what does that mean? So this is going to be 2 and this is 0. So your sine wave is not around 0. What can you do? Well, if you think about it, this is just sine t plus cos 0, right? Because cos 0 is 1. Now, let's say we want to make it all in terms of sine. Actually, let's add omega in there right now. So we have sine omega t plus cos omega t, where omega is 0, so that means it's sine, well, it's 1 here, and this in cos, it's 0t. Makes sense? And you have to remember that sine of x is just cos of x plus pi over 2. This might be a plus or a minus, I'm not sure. I believe it's a plus. Anyway, so sine x is just cos of x pi over 2. So it's just a phase-shifted function of the same thing. So you have sine 1t plus sine 0t plus pi over 2. But this pi over 2, when we look at frequency, doesn't really matter, so we can leave it as cos. But let's have it as sine just to keep things very the same. Let's keep it the same. So now let's draw the frequency graph. And the frequency graph's going to look a little bit weird, because right now we only had like one line spiking up. But in this it's a little bit different. We have at 0, because we have omega equals 0 here, and we also have omega equals 1 here. So that means we have two spikes in the frequency, or omega, graph. And actually, if we look at this, amplitude is going to be 0.5 for each. So this is 0 frequency and 1 frequency. So this one over here is this, and this one is this. And why is this 0.5 there? Well, if you think about it, half the function is made up of this, and half the function is made up of this. If we had different weighings, so let's say we had this moved up to 2. So let's actually draw this. So let's say this was at 5. So that means your sine wave looks like this, kind of. Right? And this is 0. So your function will actually look like sine 1t plus 5 sine 0t plus pi over 2. Right? And actually, this would look a little bit different. This would look like this and this. And why is that? Because the 5 is in front of the 0 frequency component. So actually, this is going to be 86, what is it, like 83.33%, I think, and this should be 16%. I'm just adding them, so it should be 1/6 for this one and 5/6 for this one. So that kind of makes sense, right? So similarly, actually, let's drill this point in. If we have this at 1, but we have a sinusoid that goes like this, where this is 3 and this is -1, we have sine 1t, but there's a 2 in front, plus just normal sine 0t plus pi over 2. So over here, we're actually going to see that we'll have this here at 0, and this here at 1. So this is going to be 66.6%, and this is going to be 33.3%. Many times for Fourier transforms, people don't really say anything for the amplitude. They don't give it a name or anything, mostly because this is relative. It's all relative. It all depends on each other. You're not actually counting how much you have of each one. You're just counting how much it has relative to the other. So, let's say we have a square wave now. Let's go back to the square wave example. So the square wave is gonna look like this. And our depiction of it is going to look like this. Right? And this is in time. And this is 1, this is -1. So our frequency graph, well, let's think about this. We have periodic sinusoids that add up, And these sinusoids are not continuous. So this is a little bit hard to understand. You can have a continuous Fourier series, but that goes really deep into it. So let's leave it for another video. But for now, what you have to think about is, first of all, is there a shift at all in the y direction? No, there's no there's no extra y-intercept. The y-intercept is at 0. So there is no, so the sine pi 0t plus pi over 2 term is going to be 0. Okay? Now the sine 1t is probably going to be very large because once you draw it over here, let's draw it in blue, it makes up a big portion of this wave. So let's say this is going to be 1 sine 1t. So now let's add another one. So let's say there's also sine 2t. What does that mean? So this is probably going to be a smaller number. Let's say 1/2. It's probably not necessarily going to be 1/2 in the actual function, but let's say it is 1/2. So that's going to allow our function to do something like this. Now that I think about it, I should have drawn it in another color, but we're going to have 1/2, and so on. The next one is probably going to be sine 3t, let's say. And this one might have, let's say, 1/3. Because each contribution you make is going to get smaller and smaller. So, let's actually draw this in frequency space. So we have the first frequency, 0, has nothing. Second one has 1. So this is frequency 1 is 1. Frequency 2 is actually going to be half of that. Frequency 3 is going to be 1/3 of the original one. And so on, and so on. So you have distinct waves, and your graph sort of looks like this. Now the problem is that you have a discrete number of waves. And in the next video, I'll go a little bit more in depth with what this means. But for now, I think this is a really good introduction into what a Fourier transform is. So this is the Fourier transform of just this. I'm not going to write it. Is this. And you can actually go back and do the inverse Fourier transform. Oops, that's not supposed to happen. So you can do the inverse Fourier transform of this to get this. Now there might be some things lost in the way, some information lost in the way. So you can actually go one way or the other using Fourier transforms. All right, so thank you for watching, and I am going to make the next video be about a little bit more in depth with Fourier transforms and maybe what they mean in physics as well, because they get very useful in physics. Thank you for watching.